So let's continue with the Nonstationary Time Series Analysis with manifold learning techniques. And I think today the main focus will be the single channel price source separation problem. So if you remember before, we talked about transabdominal maternal ECG signal, and the goal was to extract the fetal ECG from the transabdominal maternal ECG, and we somehow formulated it into a single channel price source separation problem. And we also want to discuss its relationship with biomedical signal processing. And this single channel price source separation, the basic idea is you have multiple components in one channel, and you try to separate all the components. That will be the ultimate goal. So if you recall, this is what I mentioned about fetal ECG and the transabdominal maternal ECG. So if you recall, we get ECG channel recording from a pregnant woman's abdomen, and you get the recorded signal, and you can see these big spikes. These big spikes, they are maternal heartbeats, but there are some small spikes, and those small spikes are fetal ECG. And our goal is that if I give you this signal, can you decompose it into the maternal ECG and the fetal ECG? That is the ultimate goal of what we will discuss today. We will not cover everything today. It will be something later, but I will at least give you an overall picture. And this is an overall algorithm, starting from the beginning to the very end. So if you remember, before we talked about the shape algorithm, which is a time frequency analysis technique. And if you combine it with the peak tracking algorithm, we can get maternal R peaks. And what we will talk today is, once we have those maternal R peaks, then we can somehow truncate the signal into pieces. And then we try to remove the fetal ECG so that we can recover the fetal ECG. We can recover the fetal ECG and the maternal ECG. And we can do some iteration to get final results. So that is the overall algorithm. And today, I will not recode this one. Also, you have known it. We'll focus on this part. This pointer is not very sensitive. Optimal shrinkage. Okay, so today we'll talk about optimal shrinkage and at least let you know some basic idea of optimal shrinkage and how it is related to the question we are working on and what we want right now. Okay. And this is the illustration of data preparation. So assuming that we have applied the shape algorithm and the peak tracking to get all the maternal ECG, all the maternal heartbeats, suppose that has been done. Then what we want is, we want to view the maternal ECG as a manifold. As a manifold. Okay, and what does it mean? Okay, and we will view the fetal ECG as the noise. As the noise. Today, we will not talk about the manifold structure, but you will see how it is, how it will be related very soon. But we will focus on how to handle part of this problem. Okay, so this is the illustration of assuming that we have clean data. That is, we already have the separation. We already get the maternal ECG. And then suppose we already get maternal ECG, you see that it is kind of relatively clean. You just have one cycle, about one heartbeat. But in practice, we do not. That is a chicken egg problem, right? Because that is what we want to recover. But we cannot recover, but we don't have it. What we have is actually the summation of maternal ECG and fetal ECG, and that is what you have in practice. So if you do a truncation, truncate the signal into pieces, then that is how the signal looks like. But underneath, that is what we have interest, the maternal cycle. As you can see, if we have the maternal cycle cleanly, we have the maternal cycles recovered, then we can get to the fetal ECG bank. Overall, it's gonna give up. Overall, the algorithm is under the umbrella called the template subtraction. And what is it? If you take a look at all this signal, you will see a very obvious pattern, right? That is, there is a big oscillation in the middle, okay, but there is a kind of small pattern nearby. But overall, that is the pattern. So we want to try to recover this pattern so that we can do something and recover the maternal ECG and get to the fetal ECG. So that is overall the template subtraction idea. And this is another illustration. So you get this transophthalmic maternal ECG, and the crosses are experts labeled fetal ECG, just to let you know how they look like from the other viewpoint. And you truncate the signal into pieces, and you put them together. That is, you save it as a matrix. And this is how it looks like. You will have the data matrix, which we call Z, and this Z matrix is actually the summation of maternal ECG and the fetal ECG. And this Z matrix, the data matrix, that we can obtain from the data is actually a summation of the underlying clean maternal ECG that we desire and the fetal ECG, which you can see there is also some kind of good pattern, but it somehow appears randomly, so we can view it as noise. And actually, we will model the fetal ECG as noise. Okay, now if you take a look, you will see that this Z matrix is actually, we can write as I use N by P. And each row indicates one maternal cycle. Okay, then what you can see is this matrix itself, N by P matrix, can actually be written as a singular value decomposition, which is very simple. Okay, but what is it? What do we see? What are we looking at right now? That will be the question we need to answer. But how about S? As I mentioned, the algorithm we'll discuss, or the basic idea over this kind of data is template subtraction. So there is some kind of template. Inside the data. And what is the template? As I mentioned, in the middle there is a QRS complex, a spike, right? So what we can say is, oh, this matrix is actually a low-rank matrix because we only need a few singular value and the singular vectors to represent what's going on. So that is the low-rank structure. Then we make an assumption. We assume the maternal ECG is actually a D-rank matrix, and the D is small. But what is D? We don't know. But we just know that the maternal ECG can be represented by a low-rank representation. And if we look at the meaning of this low-rank structure, you will see that, suppose I use S, right? S is this guy. And this guy, I write it, suppose, let's make assumption D is 1, which is perfect, okay? Only rank 1 matrix, very easy. Then what you have, according to the formula, is sigma U V transpose, right? Sigma is positive. Now how to do the interpretation of this U and the V matrix? Now you will see that this U is an n-dimensional vector. V transpose, this is U, okay, this is V transpose, this is a p-dimensional vector. And what are you looking at is, this is actually a pattern. This is actually a pattern. And the entry of each U, is the strength. Okay, and if I write it in a more precise way, for example, I want to look at the I cycle, so I put EI transpose. This means I want to study the I cycle. So this is EI transpose, this is N, this is P. EI transpose, then you will get EI transpose here, isn't it? And then what you get will be this guy, but you have, and this is EI transpose, then what you get will be U, well, this is a sigma here, and this is a sigma U I V transpose. So what it means is, suppose D is 1, there is only one pattern, okay? Only very, very basic one. One pattern, or I shouldn't say one pattern. I should say, suppose rank is 1. Rank is 1. And this rank is 1, the interpretation is you will have the pattern saved in in V, and this describes the pattern. And the U, the left singular vector, will describe the strength of each single cycle. And suppose D is greater than 1, then it just says that, oh, you will have D different VL, or D different kind of right singular vectors that will give you the information of the pattern, and U here will give you the strength of each cycle associated with which singular vector, right singular vector, and the sigma L is the global strength of each singular vector. So you can view V, this guy, the right singular vector, as an adaptive basis. That is, it is a basis because remember, UL and the UK will be orthogonal. So you can view V1 up to VD as a basis, as an orthogonal basis in a high-dimensional space. But this basis is determined adaptively from the data. It is something very similar to Fourier basis, but it's different. Not really Fourier basis. Okay? And now, I have talked about this maternal ECG and this structure. How about sigma, the noise? Okay? Will there be any structure here? If you look at this, and I claim it is noise, then a first question you may ask is, noise? Come on, if it is a noise, right? Why do we see some kind of pattern, isn't it? Is it Gaussian white noise? Doesn't look like Gaussian white noise, isn't it? So what is it? How should we model it? Okay, the final part is the N and the P. In the lecture today, we will focus on the condition that N is proportional to P. That is, we will assume, I may need this later, but okay. So this, the meaning is P depends on N, such that P divided by N will go to some constant. Okay, that is the meaning of N proportional to P. That means the dimension of the data or each cardiac cycle will grow as the number of the cycles increase. Okay, and the relationship is linear. And there will be some immediate questions you may come out. That is, what about if you have a very, very long recording, right? Well, you can say that, we assume or make an assumption that P, okay, will grow as N increases. That is because of the advances of technology, right? Because we have a higher sampling rate data and we have higher resolution information, etc. But well, we can record a very, very long signal, right? In this setup, then N can be very, very large. Now, what will happen? And that will be the situation we'll discuss later. And this is related to the manifold denoise problem. But right now, let's make an assumption that N is proportional to P. And later on, when we talk about the case when N is much, much larger than P, there will be an extension of what we discussed here. And when we discuss N is much greater than P, this is actually something, this framework is actually something we still need. Okay, we will see this part in a bit. Oh, well, probably not today. So the goal, what is the goal? I have told you a lot about the motivation and the model. So what do we want to do? What we want to do is, I give you a noisy data Z, and I have told you it has a singular value decomposition. And what we want is, okay, from this singular value decomposition, can we maybe do some denoise? That is the matrix denoise. And maybe after this denoise, it will be a very nice pattern of or a very nice recovery of the maternal ECG. Okay, that will be the goal. Suppose we can achieve it. After applying denoise algorithm, and we get the maternal ECG back very well. Suppose we can. Then what we can do is we can patch everything together to get the maternal ECG, and we subtract the transabdominal maternal ECG. Sorry, we subtract the maternal ECG from the transabdominal maternal ECG, and get the rough fetal ECG. This is called rough because the data, as you can see, what we get in the remaining part will not only be fetal ECG, but also the true noise. And our goal is to further iterate the algorithm and recover the fetal ECG. That is, we will further remove the noise, so that we can recover the fetal ECG. Okay, so that will be the overall structure.